Yesterday, one of you asked me the question of the distance between not a point on the geodesic, but two geodesics. So the answer is not very much complicated. It is the following proposition. Consider eta distant from eta prime and phi distant from phi prime in the boundary, and the reference point, any reference point, in HD. So the picture could be like that. And the question is to find the distance here, like that. So the answer is, the two geodesics are of course eta prime and phi prime. These ones are there. Then the hyperbolic cosine of this distance is computed by the following fraction: square root of eta p phi p multiplied by eta prime p phi prime p plus you exchange the both extremities, so you will have this and divided by the square root of eta p eta prime p phi p phi prime p. I will call the notation when you have eta here and p here, you find here, taking p orthogonal, this vector is eta p. For example, you have eta E naught equal E naught plus u for u in the sphere S d minus 1. So you find eta E naught, eta prime E naught, for example. This is the same as 1 plus u prime. If you want to express this with these coordinates, for example. So you have an exact formula valid for any pair of geodesics. And the computation is not very much complicated. Using the previous result, you have only to fix this geodesic and to parameterize the second one by some point Q and write the distance I explained yesterday between this point and this geodesic, and then you have only to minimize. And this does not depend on the reference point, of course. The reference point P has not to be mentioned on the picture. It does not depend on it. Now I come to the physical interpretation. This is done in special relativity. Since, of course, the Minkowski space is the framework for special relativity. And then the Minkowski space will be seen as the space-time. And the isometries are the change of frame. Now to any V in RD such that its norm, Euclidean norm, is strictly less than 1, I associate the boost rho index V theta, this thing, this is the inverse hyperbolic tangent of the norm here, and I conjugate with where rho V in SOD is such that rho V E1 equals V divided by its Euclidean norm. I recall that it does not depend on the choice of rho V set in this way, because again I have some indetermination by SOD minus 1 part, which commutes with this one, so it doesn't matter. Now, the Cartan decomposition can be written any G in base O1D can be written by this. I denote it by B indexed by V, B like boost indexed by V. This is a boost, of course, since being a boost does not depend upon a conjugation, of course, within the group. And this is an elementary boost. And the Cartan decomposition is equivalent to saying that it is always possible to express any element in the group as a product of such BV and rho with some rotation rho in SOD. And remark, it is very easily computed that G E naught, the first canonical basis vector, is simply E naught plus V divided by 1 minus square norm of V. Now, I shall say that a frame beta twice has velocity, relative velocity V with respect to another frame beta prime when we can write this one as the other one multiplied on the right by such an element in this form. With rho again in the proposition. This is addition rule for velocities. The addition rule for velocities is written as when composing two such boosts, call them U and V in this order. This will be of this form. This is a general statement of Cartan decomposition. I can write it in this form, and the addition rule is telling which is W. W as the following expression. I write U point V to denote the usual Euclidean inner product. For us, then it is the same height as the opposite of the Lorentz pairing for vectors in Rd. V, U, R in Rd. So the exact expression is 1 plus U point V divided by square norm of U, U, like that, plus square root 1 minus U square times V minus U point V over U square U. And this of the denominator here. This is the exact expression, the exact addition rule for velocities. This is a simple matter of computation. then I shall consider the motion of a particle of unit mass, say. This is it is described by a C1 time-like path, which is very important, it's crucial for point mass that his path be time-like. This amounts to say that he cannot go beyond, travel beyond the velocity of light. Here in my convention, here with my units, the velocity of light is 1. This is a normalization from the very beginning, since the light cone has this equation. So, I denote it by Cs, say for S positive, and I always can choose the parametrization, parametrized by arc length. Arc length is called in relativity theory proper time. This is the proper time of the particle, and this is S. So it means only that the derivative with respect to S, I denote with a point, as physicists do, belongs to the hyperbolic space. This amounts exactly to saying that. So, the motion of some particle of unit mass is only some C1 time-like path. Time-like, this is linked also to this. This is a C1 path, such that you have this crucial property. The derivative at any time belongs to the hyperbolic space. This is the velocity d plus 1 velocity. It is called in this way by physicists. Usually for physicists d equals 3, of course, but for me it does not matter. So I fix now a frame given a fixed frame beta. We can write, I give a name to coordinates merely. Style S equals T of S beta naught plus some for G going from 1 to D of denoted by X So this only means that I gave those names to the coordinates in the frame beta. Of course, I can. And this one, I denote also by tau, can be interpreted as the absolute time in the frame beta. In relativity theory, you have not absolute time given from the very beginning. It can make sense only by fixing a frame. And it is not the same if you are changing the frame, of course. The only interesting time is proper time for some motions for a particle. And if I'm considering the vector z indexed by tau, this tau, to be the vector x indexed, so I take t minus 1 of tau, remark, which is useful to define that, S, the map S gives T of S is increases. And is continuous, of course. Then I have a reciprocal map, which is well defined. And this thing is the trajectory in the frame beta. This is the apparent trajectory of the motion in the frame beta. This belongs to RD. Since only this vector, the coordinates run from 1 to d, this vector changes time. Now you have some elementary formulas from this. If I'm deriving it, V tau be defined, let V tau be the derivative with respect to tau of this trajectory. Of course, by the chain rule, very simply, this is the same as x point s over the derivative of t of s, and because of the condition to be parameterized by arc length, this one, the velocity belongs to the hyperbolic space. This is the same as this. This is the same. This being equal to this is only the fact that the velocity is belonging to the hyperbolic space. So, equivalently, of course, it is very straightforward to solve. I have x point s equal to v tau over square root of 1 minus v tau squared. And you have also the beta energy, which is T prime of S, and for the same reasons, like here, this is this quantity, which is of course very famous in special relativity. This is analogous to an energy, but in the frame, under consideration. And thus, writing the same things again, I have this is beta naught plus the sum from G equal 1 to D of V G to beta G divided by this same quantity. And I can also observe that the norm of Vito happens to be the hyperbolic tangent of the distance between beta 0. This is very easily deduced from such an expression, for example, and side point S. And of course, this is strictly less than 1. Again, we see that this velocity has to be less than that of light. I make now the link with geodesics. So the link to geodesics. I recall once again my operation of projecting onto a light ray. Always the same picture. Eta here, and say dot xi s here, and here it's orthogonal, and I consider this vector, which I denote by G psi point psi dot S of eta. Before I add the notation, last time I denoted it rather by this notation. I take this one now for convenience, for the ease of writing. And so G dot psi S of eta is the space-like vector of pseudonorm -1 in psi point S orthogonal, such that I'm only recalling this the definition one can see by interpreting the picture, such that the sum of psi point, psi dot S and this J belongs to eta, is uniquely defined, and I have the following proposition. Given eta fixed in the boundary, a time like C2 pass time like, of course, again, psi S parameterized by proper time. So this is the motion of a particle as before, and this satisfies the differential equation double dot psi S equal J psi dot S of eta for any S, of course, if only if it satisfies the following equation, dot psi S eta equal to dot psi 0 eta theta S. This means that the vector, the velocity psi dot S runs the geodesic at unit speed, the geodesic determined by the initial velocity and the asymptotic direction eta. So you have a move like that. It's not easy move. The picture is easier in the Poincaré plane. If I am putting eta here and here tangent vector like that, this means that after time S, psi point S is this vector. And interpretation of the equation looking at what is over there. This is that the motion is uniformly accelerated in the asymptotic direction eta. So, being uniformly accelerated in some direction at infinity, this this happens to be equivalent to run a geodesic at unit speed for a motion particle. And this is not difficult to prove. I'm fixing beta, the frame, such that beta 0 is the initial velocity and beta is pointing at eta, meaning that the sum of the two first vectors belongs to the direction eta, and we can always write psi prime psi dot s as beta t z s 0. This is always possible. This is only saying that my affine group operes transitively on the hyperbolic space. So this is only saying that for some Cs as usual belonging to that, the upper space. Then we have directly my second hand side, my right hand side, is then merely the same thing but the first vector style. So the equation is equivalent to simply d over ds of beta t zs 0 equals to beta t zs 1. And here, this is the same as beta tilde t zs e0. Here, e1. So this equation is equivalent to the same without beta. Beta disappears. And we already encountered this equation when I presented the geodesics. They verify this. So obviously there is a unique solution given the starting point, the velocity at time 0, and so the only possibility is that T zs is equal to theta s, and so I'm done. Now I give also a link to our spheres to complete this picture. Proposition. Consider two particles with motions given by C prime S and CS, parameterized as above. Over time, S and uniformly accelerated as before. In the direction of the same eta, the bond line. Then the vector difference between both converges as S goes to infinity if only if they start, both motions start on the same Rho sphere. Based at eta. Moreover, if this happens, this belongs true at any time. This remains true at any proper time. Only the Rho sphere depends on S here. So this gives physical meaning to Rho spheres.
So time is redundant. Times.
No, it's time. No. I do not begin at the right time. The next section. In the next section, I present the models of Poincaré. You observed that sometimes I was using a different way of depicting the things. This is actually in such a model. You have two such models. First, the ball model. Is obtained by performing a stereographic projection from minus P naught onto the unit ball BD. I draw a picture. So HD here. Here is E naught and minus E naught. And here RD. Zero. And I take a point. Here, maybe it's not the best color. I think some point, say, B here on the hyperbolic space, and I stereographically project onto the ball, which is here. And I obtain some point here, say U here, and no, I call this one P. I usually denoted by P the points of the hyperbolic space, and this one by B, like the ball, big B. And it is very easy to compute what exactly occurs, writing P in this form with a hyperbolic sine and cosine in HD. I map it to B equal hyperbolic tangent of R over 2 times U, which belongs to BD. Then proposition. This is not a very complicated map, so computations are not difficult. And the result is that in the ball model, geodesics appear as either diameters or circles, circles orthogonal to the boundary SD-1, intersected, of course, with BD. So you have either a diameter or orthogonal circle like that. These are exactly the geodesics in this model. And all spheres appear as spheres included in the ball and tangent to its boundary SD-1. So the horosphere looks like that. And here this will be eta. Of course, the boundary delta HD is mapped onto SD-1, as is clear on the picture. So the boundary, the circle bounding the ball is actually at infinity. Time?
5 minutes, sorry, I was confused.
the other model, as famous as the ball model, and as useful, is the half-space model, upper half-space. Both are due to Poincaré. Now, the upper half-space model, this is d minus 1 cross r plus star, is obtained from the preceding one, from the ball, by performing an inversion with ball E1. So this amounts to send, to throw this point, boundary point, to infinity. And the analytical expression of this inversion is to the point P of BD, I associate Z having these coordinates and defined by E1 plus, I am writing the expression of the inversion, is only like that, and this belongs to this model. E1, this is not the same. Here, this is E1 in this space. And equivalently, it is very easy to solve, of course. Y will be 1 minus B squared over B minus E1 squared, and xj is 2bj over the minus 1 squared for j between 2 and b. And proposition, I finish with that for today. The description is not complicit. Before giving the description, a fact is interesting and striking, I think. The above, these ones, coordinates x, y, are precisely the Poincaré coordinates already encountered. These are the same. This is not obvious, this is a result of the computation. And geodesics appear either as vertical half lines or as circles, orthogonal, half circles, orthogonal to d minus 1, which is the boundary. I finish and I draw the picture. spheres appear either as horizontal lines or as circles, spheres tangent to the boundary d minus 1. So the picture, once again, is very simple. These are geodesics. And all geodesics are like that. And this is a rho sphere. Or this. And here you have d minus 1, which is the model for the boundary plus the point at infinity, actually. And so the model for HD is this upper space. This. There is nothing below. And as in the ball model, of course, the boundary is at infinity. The distance between the point here and here is infinite. So I finish for today. Just one more explanation, very short. It is very easy to deduce this proposition from the preceding into the ball model, since an inversion is conformal. So you transform, of course, lines and circles into lines and circles.
If not, so you explained to us if you one model and now another two models, there is some false model that is commonly used?
Some?
False model. 1, 2, 3.
There is a false one, yes. The Klein model projective. This is projective model. It is not so used. But there is a fourth one, exactly. I don't know any fifth one.
Okay.